Every star you have ever seen is falling in the same direction. Not randomly, not slowly. The entire Milky Way and everything around it is being dragged through space at more than 600 kilometers per second towards something we have never been able to look at directly. In 1988, 7 astronomers confirmed that this motion was real, affecting not just our galaxy, but hundreds of others across a volume of space hundreds of millions of light years wide. The source required a mass tens of thousands of times greater than the Milky Way. It could not be seen in any optical telescope. It was not hidden by distance. It was hidden by our own galaxy, a quarter of the sky, swallowed by dust and stars. For nearly 2 decades, no one could prove what lay behind that blind spot. Then, in the mid-1990s, X-ray and infrared surveys cut through the obstruction and revealed a landscape far stranger and far larger than anyone had predicted. What they found was not one concentration of mass, but a chain of them, each one pulling the last, stretching across billions of light years of space, with our galaxy caught in the current. We will trace the discovery, unravel the architecture, and follow the flow to its source. If this kind of content matters to you, a like or a subscription goes a long way. The sky is not still, nothing is. The universe has a temperature. It is extraordinarily cold, just 2.725 degrees above absolute zero, and it is everywhere. In every direction you point a sufficiently sensitive instrument, there it is. A faint thermal glow, uniform and ancient, filling all of space. This is the cosmic microwave background, the oldest light in existence. It was released roughly 380,000 years after the Big Bang, at the moment the universe cooled enough for atoms to form and photons to travel freely for the first time. Those photons have been travelling ever since, stretched by the expansion of space from visible light into microwaves, carrying with them a snapshot of the infant universe. For decades after its discovery in 1965, the cosmic microwave background appeared almost perfectly smooth, uniform in every direction to an extraordinary degree. But perfection in science is always worth questioning. And when physicists began building instruments sensitive enough to detect variations of just a few thousandths of a degree, a pattern emerged. One side of the sky was slightly warmer than the other, not by much, roughly 3.4 millikelvin, but the signal was consistent and unmistakable. A gentle gradient, one hemisphere hotter, the opposite hemisphere cooler, with a smooth transition between them. This is what physicists call a dipole anisotropy, and its cause is deceptively simple. It is a Doppler shift. If you are moving through a field of radiation, the radiation ahead of you gets compressed, pushed to slightly higher energies, slightly higher temperatures. The radiation behind you gets stretched, slightly cooler. The cosmic microwave background is not warmer in one direction because it was emitted that way. It appears warmer because we are moving toward it. The idea that this motion could be measured was proposed as early as 1967 by the physicist Dennis Sciama, who reasoned that if the cosmic microwave background truly fills all of space, then any observer moving through it should see exactly this kind of asymmetry. It was a prediction waiting for the instruments to catch up. Early measurements through the 1970s by Paul Henry, and later by David Wilkinson and Brian Corey at Princeton, provided the first tentative detections. But the definitive measurement came in 1977, when George Smoot and his team at Lawrence Berkeley National Laboratory flew differential microwave radiometers aboard a NASA Ames U-2 jet, a high-altitude spy plane repurposed for science, cruising above most of the Earth's atmosphere to minimise interference. What they found was striking. The solar system is moving at approximately 370 kilometers per second relative to the cosmic microwave background. But a large fraction of that velocity is simply the Sun's orbit around the centre of the Milky Way. When you subtract that orbital motion, when you ask not how fast the Sun is moving within its galaxy, but how fast the galaxy itself is moving through the universe, the number does not go down, it goes up. The Milky Way, along with the entire local group of galaxies that surrounds it, is moving at roughly 630 kilometers per second. That is more than 2 million kilometers per hour. And it is moving in a very specific direction, toward a region of sky near the constellation Leo. This was not expected. The expansion of the universe should be carrying everything apart, smoothly and uniformly. There should be no preferred direction, and yet here was the Milky Way, racing through space at a speed that could not be explained by any nearby concentration of matter that astronomers could see. Something enormous, something invisible on every existing sky survey, was pulling us. The cosmic microwave background had given up a secret. Now someone had to explain it. That explanation would take more than a decade to assemble, and it began not with the cosmic microwave background at all, but with a deceptively simple idea about how galaxies move. In an expanding universe, every galaxy is receding from every other galaxy. The farther away a galaxy is, the faster it appears to move away from us. This is Hubble's law, the foundational observation of modern cosmology, first established in 1929. If you measure the redshift of a distant galaxy, the degree to which its light has been stretched toward longer, redder wavelengths, you can calculate how quickly it is receding, and from that, you can estimate its distance. It is an elegant system, and for most of the 20th century, it worked beautifully, but it is also an approximation. Hubble's law describes the average behaviour of the universe. It tells you what a galaxy should be doing if nothing else were acting on it. In reality, galaxies are not just riding the expansion. They are also being tugged by the gravity of everything around them. Nearby clusters, distant superclusters, vast concentrations of matter scattered unevenly across the cosmos. These gravitational influences create additional motions on top of the expansion. Astronomers call them peculiar velocities, and they are the key to everything that follows. A peculiar velocity is what remains when you subtract the expected recession speed from a galaxy's observed speed. If a galaxy is receding slightly faster than Hubble's law predicts, it is being pulled away from us by something beyond it. If it is receding slightly slower, something between us and that galaxy is pulling it back toward us. The deviations are small compared to the cosmic expansion itself, typically a few hundred kilometers per second against a backdrop of thousands, but they carry an extraordinary amount of information. Peculiar velocities are fingerprints of mass. They reveal the invisible architecture of the universe by telling you not where galaxies are, but where gravity is strongest. In the early 1980s, a team of 7 astronomers set out to map these motions systematically. Donald Lyndon Bell at the University of Cambridge, Alan Dressler at the Carnegie Observatories, Sandra Falber at the University of California, Santa Cruz, David Burstein at Arizona State, Roger Davies, then at Kitt Peak National Observatory, Roberto Turlevich at the Royal Greenwich Observatory, Gary Wegner at Dartmouth College. They came from different institutions and different backgrounds, but they shared a single ambition: to measure the peculiar velocities of hundreds of elliptical galaxies across a wide swathe of the sky, and use those motions to infer the distribution of matter pulling on them. To do this, they needed a distance measurement that was independent of redshift. If you only know a galaxy's redshift, you cannot separate the expansion from the peculiar velocity. The two are tangled together. You need another way to estimate how far away the galaxy actually is, so you can compare that true distance to what the redshift predicts. The difference is the peculiar velocity. The team used a relationship between the intrinsic brightness of elliptical galaxies and the speeds at which stars orbit within them, a technique that allowed them to estimate distances with enough precision to detect deviations of a few hundred kilometers per second. It was painstaking work, nearly 400 galaxies, each one requiring careful spectroscopic observation and photometric measurement. What emerged from the data was not a random scatter of velocities. It was a river. Across the entire survey volume, a region spanning hundreds of millions of light years, galaxies were streaming in the same direction. Not all at the same speed, but all toward the same destination. The motion was coherent, large-scale, and unmistakable. Something was pulling them. Something massive, something concentrated, and something that did not appear on any existing map. Their landmark paper, published in the Astrophysical Journal in 1988, placed the source of this attraction behind the plane of the Milky Way at a distance of roughly 150 to 250 million light years in the direction of the southern constellations Triangulum Australe and Norma. Alan Dressler gave it a name that captured both its power and the mystery surrounding it. He called it the Great Attractor. The response from the wider astronomical community was immediate and divided. At a workshop in Santa Cruz, California in 1986, where preliminary results had already been presented, theorists were alarmed. The idea that such a large region of the nearby universe was participating in a single coherent flow toward an unseen mass concentration was difficult to reconcile with the prevailing models of how structure should be distributed. Observers were skeptical for a different reason. The measurements were difficult, the statistical uncertainties were real, and the possibility that systematic errors might be mimicking a genuine signal could not easily be dismissed. Astronomer Amos Yahil, struck by the team's willingness to challenge the conventional picture, dubbed them the Seven Samurai, a name that stuck. But the data held. Independent measurements from other groups, using different techniques and different galaxy samples, began to confirm that the streaming motion was real. The Milky Way was not simply drifting. It was being carried, along with everything around it, toward a specific point in space. A point that no optical telescope could see. The question was no longer whether the Great Attractor existed. The question was what it was. And answering that would require finding a way to see through the one obstacle that had kept it hidden from the very beginning, the Milky Way itself. Look up at the night sky on a clear evening and you see stars. Thousands of them scattered across a black canvas. But look more carefully, and you will notice something else. A pale, luminous band arching from horizon to horizon. That band is the plane of the Milky Way, our galaxy seen edge on from within. It is beautiful. It is also, for anyone trying to understand what lies beyond it, a catastrophe. The Milky Way's disk is not just stars. It is dense clouds of interstellar dust, microscopic grains of carbon and silicate, each one smaller than a human hair, packed together in quantity sufficient to block the light of everything behind them. Mixed among the dust are vast reservoirs of molecular gas, and, closer to the galactic centre, such a dense concentration of foreground stars that individual sources blur together into an unresolvable haze. The result is a broad swath of sky, extending roughly 20 degrees on either side of the galactic midplane, in which optical telescopes are essentially blind to the distant universe. Astronomers call it the zone of avoidance, a name coined not as metaphor, but as practical instruction. Early extragalactic surveys simply avoided it. There was nothing to see. That is not quite true, of course. There was plenty to see. It was simply unreachable. The zone of avoidance covers approximately a quarter of the entire extragalactic sky. Imagine a map of every galaxy, every cluster, every filament in the observable universe, and then imagine erasing a quarter of it. Not randomly scattered gaps, but a single continuous belt running through some of the most important regions of the nearby cosmos. The distortion this introduces is not subtle. Large-scale structure surveys, which depend on mapping the three-dimensional distribution of matter as completely as possible, are left with a blind stripe through the middle of their data. And the great attractor, the mass concentration that the Seven Samurai had inferred from the motion of hundreds of galaxies, lay directly behind it. The coordinates placed it in the direction of the southern constellations Triangulum, Australe, and Norma, a region deep within the zone of avoidance, where dust extinction is severe and star crowding is at its worst. Astronomers could measure the gravitational influence of whatever was there. They could see the galaxies around it moving, feel its pull in the numbers, watch the streaming motion converge toward a specific region of sky. But they could not look at it. It was as if the most important room in a building had been bricked shut, and the only evidence that anything lay behind the wall was the sound of something enormous breathing on the other side. This was not a temporary frustration. It persisted for years. Through the late 1980s and into the early 90s, the Great Attractor remained a gravitational signature without a visible source, an invisible centre of mass inferred entirely from the behaviour of galaxies around it. And for some astronomers, that invisibility was precisely what made the whole idea suspect. If you could not see it, how could you be sure it was there? The problem was not merely that light was dimmed. In the densest parts of the zone of avoidance, optical extinction can exceed 25 magnitudes, meaning the light from a background galaxy is reduced by a factor of 10 billion before it reaches us. At that level of attenuation, even the brightest galaxy clusters are indistinguishable from the blackness between stars. And where the dust thins enough for some light to leak through, a different problem emerges: source confusion. Millions of foreground stars fill every field of view, and distinguishing a faint, reddened galaxy from a dim Milky Way star becomes an exercise in forensic astronomy. Entire careers were spent on this boundary, painstakingly classifying objects one by one, separating the nearby from the impossibly distant, building maps from fragments. The answer, when it finally came, did not arrive through better optical telescopes or clearer skies. It arrived through a shift in thinking, a decision to stop looking at the universe in visible light and start listening to it in wavelengths that dust cannot block. The key insight was straightforward. Dust absorbs and scatters visible light. The wavelengths human eyes are built to detect, and the wavelengths most optical telescopes are designed to collect. But the electromagnetic spectrum is vastly wider than the narrow band we call visible. Shift to longer wavelengths and the dust becomes increasingly transparent. Near-infrared light, with wavelengths roughly twice those of visible red, passes through moderate dust columns with significantly less attenuation. Radio waves, with wavelengths measured in centimetres or metres, ignore the dust entirely. X-rays, at the opposite end of the spectrum, wavelengths thousands of times shorter than visible light, also penetrate the galactic plane with relative ease, because the dust grains are too large to interact efficiently with such short wavelengths. The universe behind the curtain had not disappeared. It had simply been waiting for astronomers to look at it differently. The 2-mass survey, the 2-micron all-sky survey, was among the first to systematically exploit this principle on a grand scale, operating in the near-infrared at wavelengths of 1.2, 1.6 and 2.2 micrometers. 2-mass scanned the entire sky between 1997 and 2001, cataloguing hundreds of millions of stars and more than 1 million galaxies. For the first time, the zone of avoidance began to thin. Galaxies that had been completely invisible in optical surveys appeared as faint smudges in the infrared data. Their ancient starlight reddened and dimmed, but no longer extinguished. The belt of darkness was not gone. It was still the most difficult region of sky to survey, but it was no longer impenetrable. Radio astronomy offered a complementary window. Neutral hydrogen, the most abundant element in the universe, emits radiation at a characteristic wavelength of 21 centimeters. This emission passes through dust as though it were not there. By tuning radio receivers to this frequency, astronomers could detect gas-rich galaxies deep within the zone of avoidance, measure their recession velocities, and begin to populate the blank zone on cosmological maps with real data. The Parkes Radio Telescope in Australia and the Dwingaloo Telescope in the Netherlands became critical instruments in this effort, conducting targeted surveys of galaxies at low galactic latitudes throughout the 1990s. But the most decisive breakthrough came from above the atmosphere. Galaxy clusters, the massive nodes where hundreds or thousands of galaxies are gravitationally bound together, are filled with superheated gas at temperatures of tens of millions of degrees. This gas, known as the intracluster medium, radiates powerfully in X-rays. And X-ray telescopes, orbiting above the absorbing blanket of Earth's atmosphere, could detect these emissions regardless of whether the Milky Way's dust lay in between. The clusters in the Zone of Avoidance projects, launched by Harold Ebeling, R. Brent Tully, and their collaborators at the University of Hawaii, became the first systematic effort to hunt for galaxy clusters hidden behind the galactic plane using X-ray data. Drawing on observations from the Rosat All-Sky Survey, a German-led X-ray satellite mission that mapped the entire sky in the early 1990s. The team identified candidate clusters within the zone of avoidance, and then followed up with ground-based spectroscopy to confirm their distances and properties. By 2005, the project had catalogued and spectroscopically verified 137 galaxy clusters in a region of sky that just a decade earlier had been a blank space on every cosmological map. Simultaneously, from the University of Cape Town, René Kraan-Korteweg and Patrick Walt were conducting something even more grueling: deep optical and near-infrared redshift surveys at the very lowest galactic latitudes, pushing into regions where even infrared observations were difficult. Their work demanded extraordinary patience. Each galaxy had to be painstakingly separated from the dense stellar foreground, its faint light extracted and measured. Over the course of decades, their surveys accumulated enough data to map the distribution of galaxies near the Great Attractor's predicted location with a level of detail no one had previously achieved. What they found was not emptiness. It was not a marginal overdensity or a modest clustering of a few dozen galaxies. Behind the curtain, exactly where the streaming motions had pointed, lay one of the richest galaxy clusters in the nearby universe. A massive, violent, gravitationally dominant structure that had been hidden in plain sight for as long as humans had been mapping the cosmos. In 1996, Kraan-Korteweg and her colleagues published a landmark paper in Nature, identifying it as the heart of the Great Attractor. It already had a catalogue number, tucked away in a supplement to the Abell catalogue that had been compiled years earlier. Its name was Abell 3627, but the world would come to know it by a different designation, the Norma Cluster, and it was about to change the story completely. The Norma Cluster sits approximately 230 million light-years from Earth, receding from us at a velocity of 4,871 kilometers per second. Those numbers place it squarely within the region the Seven Samurai had identified as the gravitational center of the Great Attractor. But numbers alone do not capture what Abell 3627 actually is. To understand why this single cluster mattered so much, you need to understand what was happening inside it. Galaxy clusters are not gentle places. They are the largest gravitationally bound structures in the universe. Collections of hundreds or sometimes thousands of galaxies held together by the combined pull of their own mass, and far more importantly, by the mass of the dark matter halo in which they sit. The Norma Cluster is among the richest of these systems. Its velocity dispersion, a measure of how fast its member galaxies are moving relative to one another, and therefore an indicator of how deep the gravitational well is, reaches 925 kilometers per second. That is enormous. For comparison, the velocity dispersion of the Coma Cluster, one of the best studied clusters in the northern sky, and long considered a benchmark for massive systems, is similar. The Norma Cluster, hidden for decades behind the dust of the Milky Way, belongs in the same category. The cluster is dominated by old, massive elliptical galaxies. Galaxies that have long since exhausted their supplies of cold gas and ceased forming new stars. These are the heavyweights of the galactic population, built through billions of years of mergers and accretion. Many of the galaxies in the Norma Cluster show signs of ongoing interactions. Tidal tails, distorted shapes, and bridges of material stretched between neighbours caught in each other's gravitational embrace. Several are powerful radio sources, their central supermassive black holes fed by the turbulent conditions of the cluster environment, launching jets of energized plasma that extend far beyond the visible edges of the galaxies themselves. One galaxy in particular captures the violence of life inside the cluster with extraordinary vividness. As it plunges through the superheated gas that fills the space between galaxies, the intracluster medium, it is being stripped. The pressure of the surrounding gas, moving at hundreds of kilometers per second relative to the galaxy, tears away its own gas reserves in a process known as ram pressure stripping. Behind it trails a remarkable tail of warm molecular hydrogen, extending roughly 20 kiloparsecs, 65,000 light-years, into the void. It is a galaxy being undressed by its own environment, its raw materials scattered behind it like a contrail. The intracluster medium itself was confirmed in spectacular fashion by X-ray observations. In 1996, Hans Bohringer and colleagues detected the Norma cluster's hot gas using satellite data measuring a temperature of approximately 7 kilo electron volts, equivalent to roughly 80 million degrees. Gas this hot does not come from stars or supernovae. It comes from the gravitational energy released as matter falls into the cluster's potential well, heating to temperatures that only the most massive structures in the universe can produce. The X-ray luminosity of this gas provided an independent confirmation of the cluster's enormous mass, estimated at roughly 10 to the power of 15 solar masses, a quadrillion suns. The Norma cluster does not exist in isolation. It sits at the intersection of a network of galaxy filaments known as the Norma Wall, a broad, sheet-like structure connecting it to the Hydra and Centaurus clusters further north, forming part of the larger Hydra-Centaurus-Norma supercluster complex. This filamentary architecture is not incidental. It is the scaffolding of the Great Attractor itself. Not a single object, but a region where filaments converge, mass accumulates, and gravity funnels the surrounding universe inward. The cluster is the densest node in this web, the point where the threads of the cosmic tapestry pull tightest. And yet, for all its mass, for all the violence and heat and gravitational authority of Able 3627, something did not add up. The streaming motion the Seven Samurai had measured, the coherent flow of galaxies across hundreds of millions of light-years, required more mass than the Norma cluster and its surrounding filaments could provide. A great deal more. The attractor was real. The cluster was real. But the story was not finished. In fact, it was about to be seriously complicated. The complication arrived in the form of a statistical ghost, an artifact of the way astronomers measure distances to faraway galaxies. It is called the Malmquist bias, named after the Swedish astronomer Gunnar Malmquist, who first described the effect in the early 20th century. The principle is subtle but powerful. In any survey that selects galaxies based on their apparent brightness, which is to say virtually every survey conducted before the modern era, there is a systematic tendency to see only the brightest objects at great distances while missing the fainter ones. This seems obvious enough. But the consequences are insidious. In a region of space where galaxies are more densely packed, you're more likely to observe galaxies that happen to be intrinsically brighter than average. If you then use those brightness measurements to estimate distances, you will systematically underestimate how far away they are, because you are comparing them to an average that includes many fainter galaxies you never saw. The effect works in reverse for underdense regions, where your sample is biased toward dimmer objects and distances are overestimated. The net result is an artificial pattern in which dense regions appear closer than they really are, and sparse regions appear farther away. When translated into peculiar velocities, this creates the illusion of a coherent flow toward the overdensity, galaxies that appear to be streaming inward, when in fact the distances themselves are wrong. In 1992, several research groups pointed out that the Malmquist bias could account for a significant portion of the Great Attractor signal. The claim was devastating. If the bias explained even half of the observed streaming, then the mass required to drive the flow would plummet. And, with it, the Great Attractor's status as the most significant gravitational anomaly in the nearby universe. For several years, the debate was fierce and genuinely unresolved. Some researchers argued that the original Seven Samurai measurements were fundamentally compromised, that the coherent flow they had detected was in large part a mirage created by the very tools used to measure it. Others maintained that while the bias was real and needed correction, it could not account for the full amplitude of the observed motion. The signal was too strong, the direction too consistent, the independent confirmations too numerous to be entirely artifactual. It is worth pausing here, because this period represents something important about how science actually works. The Great Attractor was not a fringe idea that had been debunked, nor was it a settled fact that had been challenged by cranks. It was a serious, data-driven claim that had been met with a serious, data-driven objection, and for a time, the two sat in genuine tension. The Great Attractor was in scientific limbo, too well supported to be dismissed, too contaminated to be fully trusted. The resolution came slowly, through precisely the kind of painstaking, methodical work that characterises science at its most honest. New surveys were designed with the Malmquist bias explicitly in mind. X-ray selected cluster samples, which are far less susceptible to the brightness biases that plague optical surveys, were used to re-examine the mass distribution behind the zone of avoidance. Independent distance indicators, techniques that did not rely on the same assumptions as the original measurements, were applied to cross-check the results. What emerged was a revised picture. The Great Attractor was real. A genuine mass concentration did exist in the direction the Seven Samurai had identified, anchored by the Norma cluster and its surrounding filamentary structures. But it was substantially less massive than the original estimates had suggested. Perhaps only 1/10 of the mass that had been inferred in the 1980s. The enormous gravitational anomaly that had once seemed capable of dragging half the nearby universe toward it turned out to be more modest than anyone had imagined. Significant, certainly. Massive by any terrestrial standard, but not sufficient. The clusters in the Zone of Avoidance project, led by Dale Kuchevsky and Harold Eberling at the University of Hawaii, provided one of the clearest reckonings. Their 2005 analysis found that the galaxies within the Great Attractor region accounted for only about 44% of the Milky Way's total peculiar motion, less than half. That number landed like a quiet earthquake. If the Great Attractor explained less than half of our galaxy's motion through space, then something else, something beyond the Great Attractor, something even further away, was responsible for the rest. The attractor was real, but it was not great enough. The pull did not stop at 230 million light years. It continued deeper into space, toward a source that was only just beginning to come into focus. The clue had been sitting in the archives for more than half a century. In 1930, the American astronomer Harlow Shapley was examining photographic plates taken with the Bruce telescope at Bloemfontein, South Africa, cataloguing the distribution of galaxies across the southern sky. Most of the sky showed a fairly even scattering, galaxies distributed in the loose, unremarkable pattern that early 20th century astronomers had come to expect. But in one region, centred on the constellation Centaurus, Shapley noticed something different. An extraordinary concentration of galaxies, denser and more extended than anything else on his plates. He described it simply as the most striking cloud of galaxies visible in the southern hemisphere, an elongated swarm stretching across several degrees of sky. At the time, the observation was noted and set aside. The idea that galaxies might be organised into structures much larger than individual clusters was not yet part of mainstream thinking, and Shapley's cloud remained a curiosity in the literature for decades. It was not until 1989 that Somak Raychaudhuri, working at the University of Cambridge with data from the automated plate measuring facility, gave the concentration a formal name, the Shapley supercluster, and began to characterise its scale. In that same year, independently, Roberto Scaramella and colleagues identified the same region as the most significant mass concentration in the nearby universe, labelling it the alpha concentration in their search for the source of the Great Attractor's pull. Two groups, working from different datasets, had converged on the same answer. The Shapley supercluster lies approximately 650 million light-years from Earth. That is roughly 4 times the distance to the Great Attractor. To put that in perspective, light that left the Shapley concentration when it was first emitted has been travelling for 650 million years, a span of time that reaches back to before the first complex multicellular life appeared on Earth. The Milky Way did not yet exist in its current form when those photons began their journey, and the structure they left behind is vast beyond easy description. The concentration contains at least 25 rich galaxy clusters, each one a gravitationally bound collection of hundreds or thousands of galaxies embedded in a halo of dark matter and superheated gas. 3 of the 5 richest clusters, within 1 billion light-years of Earth, reside within the Shapley supercluster. Its total mass is estimated to be equivalent to roughly 10,000 Milky Way galaxies. Among the 220 superclusters that have been identified and catalogued in the observable universe, the Shapley concentration is the single most massive, and it is pulling us, not just us, not just the Milky Way or the local group, or even the broader Virgo supercluster. The Great Attractor itself, the entire Norma cluster and the filamentary web surrounding it, the very structure that had seemed like the end of the story, is falling toward the Shapley concentration. The attractor is being attracted. This is one of the most vertiginous ideas in modern cosmology. It is a nesting of gravitational influence that operates on scales the human mind was never designed to hold. The Milky Way falls toward the Great Attractor at hundreds of kilometers per second. The Great Attractor, in turn, falls toward the Shapley concentration at its own velocity, carrying everything within its gravitational basin along with it. Structures pulling structures over distances measured in hundreds of millions of light years, in a cascade of motion that stretches across a significant fraction of the observable universe. And the motion is not chaotic, it is ordered, coherent. A river flowing into a river flowing into a river, each one larger and more powerful than the last. The Kochevsky and Ebeling analysis that have reduced the Great Attractor's mass to 1/10 of its original estimate simultaneously revealed the Shapley concentration's true significance. If only 44% of our motion was attributable to the nearby Great Attractor region, then the remainder pointed unmistakably toward a far larger gravitational source. The bulk flow, the large-scale streaming motion that the Seven Samurai had first detected, did not terminate at the Great Attractor. It passed through it, continuing outward towards Shapley, gathering momentum from the most massive collection of matter in the local universe. More recent work has only deepened this picture. In 2024, an analysis using the Cosmic Flows 4 dataset, the most comprehensive catalogue of galaxy peculiar velocities ever assembled, found a 60% probability that Laniakea, the supercluster we call home, is not an independent basin of attraction at all. It may instead be a tributary of the far larger Shapley Basin, a substructure within a gravitational watershed potentially 10 times the volume of Laniakea itself. If that probability holds, then the Great Attractor is not even the centre of our own supercluster in any ultimate sense. It is a local depression on the slope of a much deeper valley, and the valley floor lies 650 million light-years away, in a cloud of galaxies that Harlow Shapley noticed almost a century ago from a hilltop in South Africa. The story had changed. The Great Attractor was no longer the final answer. It was a waypoint, a concentration of mass significant enough to shape the motions of thousands of nearby galaxies, but itself caught in a larger current. The question was no longer simply what is pulling us. It had become something more unsettling and more interesting. How deep does the pull go? And is being pulled the only force at work? For most of the 20th century, the word supercluster meant something relatively simple. It described a region where galaxy clusters were more densely packed than average, a visible overdensity on the sky, defined by what you could count and where you could count it. The boundaries were drawn by eye, based on the apparent distribution of galaxies in surveys. It was a useful label, but it was imprecise. Two astronomers looking at the same region of space could draw the boundary in the different places, and both be equally justified. There was no physical principle underlying the definition, no way to say where one supercluster ended and another began. In September of 2014, a paper published in Nature changed that entirely. R. Brent Tully at the University of Hawaii, Helene Courtois at the University of Lyon, Yehuda Hoffman at the Hebrew University of Jerusalem, and Daniel Pomerades at CEA Paris-Saclay proposed a new way of thinking about superclusters, not as regions of high density, but as basins of gravitational attraction. The concept was drawn from an analogy so natural it seems, in hindsight, almost obvious. Think of rainfall on a landscape. When rain hits the ground, it flows downhill, following the contours of the terrain until it collects in a river, a lake, a drainage basin. The boundaries between drainage basins are ridgelines, elevated terrain where water on one side flows east and water on the other side flows west. The basins are defined not by where the water accumulates, but by the direction the water flows. Galaxies, Tully and his colleagues argued, behave in exactly the same way. In an unevenly distributed universe, every galaxy experiences a gravitational pull towards the nearest and most massive concentration of matter. That pull creates a velocity, a peculiar velocity, the motion left over after you subtract the expansion of space. Map those velocities across a large enough volume and you can trace the flow fields, the gravitational landscape through which galaxies are moving. Regions where all flows converge toward a common centre form a basin of attraction. The boundaries between basins are the surfaces where flows diverge, the cosmic equivalent of continental divides. Using the Cosmic Flows 2 catalogue, a dataset containing the measured peculiar velocities of more than 8,100 galaxies, and a mathematical technique called Wiener filter reconstruction, the team mapped the flow field of the local universe and identified the basin we inhabit. They named it Laniakea, a Hawaiian word meaning immense heaven. The name was suggested by Nawa'i Napoleon, an associate professor of Hawaiian language at Kapiolani Community College, in honour of the Polynesian navigators who read the stars and currents of the Pacific to cross vast stretches of open ocean. Laniakea is immense by any measure. It spans approximately 500 million light years and contains roughly 100,000 galaxies. Within its borders lie structures that had previously been considered separate: the Virgo supercluster, the Hydra Centaurus region, the Pavo Indus filament, and the Great Attractor itself. All of them, it turned out, are part of the same gravitational watershed. Every galaxy within this volume, including our own, is flowing inward along the contours of the density field toward a common centre. And that centre, the valley floor, the lowest point in the gravitational landscape, is the Great Attractor. The idea that galaxies are organised into superclusters was not itself new. Gérard de Vaucouleurs had argued as early as the 1950s that the Milky Way belonged to a larger structure he called the local supercluster, an idea that was controversial for decades and only gradually accepted. What Tully and his colleagues had done was give that intuition a rigorous physical foundation. Superclusters were no longer just overdensities to be sketched on a map. They were dynamical objects, defined by the motions of the galaxies within them. The discovery reframed the Great Attractor completely. It was no longer a mysterious anomaly lurking behind the Milky Way. It was the gravitational heart of our home supercluster, the point toward which the entire basin converges. Its significance had not diminished with the downgrading of its mass. If anything, it had grown. The Great Attractor was not just a cluster pulling nearby galaxies. It was the organising centre of a structure 500 million light years across. But Laniakea came with a caveat that carried its own kind of weight. The supercluster is not gravitationally bound. The flows that define it are real, and the convergence toward the Great Attractor is genuine. But the accelerating expansion of the universe, driven by dark energy, is stronger. Over cosmic timescales, Laniakea will not hold together. Its galaxies will not reach the centre. The basin will flatten, the flows will slow, and the structure will disperse. Laniakea is a transient arrangement, a snapshot of gravitational influence at the present epoch, preserved in the motions of galaxies but destined to dissolve. It is immense, and it is temporary. That understanding that the largest structure we call home is not permanent casts the entire story of cosmic motion in a different light. But even as the picture of gravitational attraction was being refined, a parallel discovery was quietly reshaping the other half of the equation. Because attraction, it turns out, is only part of the story. In January of 2017, the same team that had defined Laniakea, Yehuda Hoffman, Daniel Pomerade, R. Brent Tully and Hélène Courtois published a new paper, this time in Nature Astronomy. The subject was not what pulls galaxies together, it was what pushes them apart. The idea is deceptively simple. In an expanding universe with a perfectly uniform distribution of matter, every point expands away from every other point at the same rate. There is no preferred direction and no net force. But the universe is not uniform. It has overdensities, regions where matter has clumped together, and underdensities, regions where matter is sparse, where the voids are. An overdensity pulls surrounding galaxies toward it through gravitational attraction. Everyone understands that, but an underdensity does something equally powerful and far less intuitive. By having less mass than the cosmic average, it creates a gradient in the gravitational potential, a slope that pushes objects away, not through any exotic force, simply through the absence of the gravity that would otherwise hold things in place. Voids push, not as a metaphor, as physics. The team's analysis revealed something remarkable. On the far side of the local group, in the direction exactly opposite to the Shapley concentration, lies an enormous underdense region. A void so vast and so empty that its gravitational influence rivals that of the greatest overdensities in the nearby universe. They called it the dipole repeller because it sits on the opposite pole of our motion through space from the attractors that pull us forward. And its contribution to the cosmic microwave background dipole, the signal that started this entire story, the warm side of the sky, is roughly equal to that of the Shapley concentration itself. The Milky Way is not simply being pulled, it is being pushed, simultaneously and from opposite directions, by forces of comparable strength. The Shapley concentration, 650 million light-years ahead, draws us forward. The dipole repeller, at a comparable distance behind, drives us away. Our motion through space, that's 630 kilometers per second, measured in the cosmic microwave background, is not the result of one tug. It is the sum of a push and a pull operating in concert across billions of light years. The method the team used to find the dipole repeller is itself revealing. They did not look for it directly. You cannot see a void the way you can see a cluster. Voids are defined by what they lack. They contain very few galaxies, emit very little light, and are nearly invisible in conventional surveys. Instead, the team studied how galaxies move. By mapping the peculiar velocity field across a large volume of space and working backward from those motions to the mass distribution that must be causing them, they could infer not only where matter is concentrated, but where it is absent. The velocity field carries the fingerprint of every mass and every void in the local universe. You just have to know how to read it. What the velocities revealed was that the bulk flow of the local universe, the coherent streaming motion that had puzzled astronomers since the 1980s, aligns more closely with the direction of the dipole repeller than with any single attractor. The void behind us is, in a sense, more responsible for the direction of our travel than the mass ahead of us. We are not falling into the future so much as being expelled from the emptiness behind. This was a profound shift. For decades, the story of the Great Attractor had been framed entirely in terms of gravity pulling matter together, mass attracting mass across unimaginable distances. The dipole repeller revealed that the story had always been incomplete. Cosmic flows are not shaped by peaks alone. They are shaped by peaks and valleys together, by what is there and what is not, by the full topology of the density field. the universe moves not only toward its heaviest concentrations, but away from its emptiest expanses. And the emptiness, being harder to see, had been hiding in plain sight. The tools that revealed the dipole repeller did not appear overnight. They are the product of a single, evolving program that has been quietly assembling the most detailed map of cosmic motion ever attempted. It is called cosmic flows, and its ambition is as straightforward as it is enormous: to measure the distances and peculiar velocities of as many galaxies as possible, and from those measurements reconstruct the gravitational landscape of the local universe. The program began modestly. Its first catalogue, Cosmic Flows 1, compiled roughly 1,700 galaxy distances. Cosmic Flows 2, published alongside the Laniakea paper in 2014, expanded the dataset to more than 8,100 galaxies. Cosmic Flows 3, released in 2016, pushed the count above 17,000. And Cosmic Flows 4, the most recent release, contains the measured distances of approximately 56,000 galaxies, grouped into more than 38,000 galaxy groups, extending outward to roughly 1 billion light-years. Each successive release has not only added more data, but refined the techniques used to extract peculiar velocities from that data, producing an increasingly precise portrait of how the nearby universe moves. The flow field that emerges from these measurements is not simple. It is a three-dimensional map of gravitational influence, a landscape of hills and valleys, attractors and repellers, currents and divides. In 2023, Alexandre Dupuy and Hélène Courtois used the Cosmic Flows 4 data to define the watershed structure of the local universe with unprecedented clarity, identifying 6 distinct superclusters as basins of attraction: Laniakea, Shapley, Perseus Pisces, Hercules, Lepus, and Apus. Each basin is a region within which all galaxy flows converge toward a common centre. The boundaries between them are the ridgelines, the surfaces where the direction of flow changes, where a galaxy on one side drifts toward one attractor, and a galaxy on the other side drifts toward a different one. Dupuy and Courtois also identified something equally important: the repellers. Within the Bootes void and the Sculptor void, they located central underdensities that actively push surrounding matter outward. And they raised a striking possibility that the dipole repeller and the cold spot repeller, previously treated as separate features, might in fact be a single, enormous, underdense region. If confirmed, it would represent one of the largest coherent structures in the nearby universe. Not a wall of galaxies or a chain of clusters, but a gulf of emptiness stretching across hundreds of millions of light-years. The program has also revealed how much remains hidden. In 2017, Renée Kraan-Korteweg and her colleagues, using the Southern African Large Telescope and the AAA Omega spectrograph, announced the discovery of the Vela supercluster, a potentially massive structure lying approximately 800 million light-years away, still partially obscured by the zone of avoidance. The Vela supercluster had gone entirely undetected in previous surveys. Its existence raised an uncomfortable question. If a structure of that scale could remain hidden until 2017, what else might be lurking behind the galactic plane? 3 years later, in 2020, Daniel Pomereed and colleagues identified the South Pole Wall, a colossal arc of galaxies stretching over 700 million light-years, curving around the southern boundary of Laniakea like an arm reaching across the sky. It subtends an arc of roughly 200 degrees as seen from Earth. The South Pole Wall had been hiding not behind dust, but in plain sight. Its diffuse structure spread across such a vast area of sky that it had simply been too large and too faint to recognise as a single coherent feature, until the flow data revealed its gravitational signature. These discoveries carry a humbling implication. Our maps of the local universe, despite decades of work and tens of thousands of measured galaxies, remain incomplete. The zone of avoidance still conceals a significant fraction of the nearby cosmos. Large-scale structures that influence the motions of galaxies, and therefore the trajectory of our own, may still await discovery. The cosmic watershed is being charted, but the cartography is far from finished. There is something else these maps reveal. Something that sits beneath every cluster, every filament, every basin of attraction, like a foundation beneath a building. The galaxies we can see, the luminous points of light that populate our surveys, are not the main story. They never have been. They are markers, tracers, bright ornaments hung on a scaffold that is itself invisible. The scaffold is dark matter, and it accounts for roughly 85% of all the matter in the universe. Dark matter does not emit light. It does not absorb it. It does not scatter it. It interacts with the rest of the universe through gravity alone. But that interaction is overwhelming. Every galaxy, every cluster, every supercluster sits within a halo of dark matter that outweighs the visible material by a factor of roughly 5 to 1. The cosmic web, the filamentary structure of the universe, with its threads of galaxies strung between nodes of massive clusters and separated by immense voids, is not drawn by visible matter. It is drawn by dark matter. The galaxies follow. The evidence for this scaffolding has been accumulating for decades. In the 1970s, Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies and found that stars at the outer edges were orbiting far too quickly to be held in place by the visible mass alone. Something unseen was providing the additional gravitational pull. That something turned out to be everywhere, not just in individual galaxies, but in the spaces between them, woven through the fabric of the cosmos at every scale. The Great Attractor, the Shapley concentration, the Norma cluster, all of them are fundamentally dark matter structures. The visible galaxies are passengers. The dark matter is the vehicle. The cosmic web itself grew from almost nothing. In the first moments after the Big Bang, the universe was nearly, but not perfectly, uniform. Tiny quantum fluctuations in the density of the primordial plasma, variations so small they amounted to roughly 1 part in 100,000, were frozen into the fabric of space as it expanded. Over 13.8 billion years, gravity amplified those fluctuations. Regions that were slightly denser attracted more matter, growing denser still. Regions that were slightly underdense lost matter to their neighbours, becoming emptier. The process was slow, relentless and cumulative, and it produced the filamentary web of matter that we observe today. The seeds of the Great Attractor were planted in the first fraction of a second after the Big Bang. Everything that followed was gravity, doing its patient work. But there is a tension in this picture, and it is one that the most recent data has made difficult to ignore. In 1986, Margaret Geller and John Huchra published the first large-scale galaxy redshift survey, the famous slice of the universe, revealing that galaxies were not scattered randomly through space, but organised into vast walls and filaments separated by enormous voids. That discovery confirmed the existence of the cosmic web. What the Cosmic Flows program has revealed, however, is that the observed superclusters, the basins of attraction mapped using galaxy flows, are an order of magnitude larger than those predicted by standard lambda CDM simulations. The theoretical models produce structure, but not enough of it. The simulated universe is lumpier than expected, or the real universe is lumpier than the models allow. This is not a minor discrepancy. It suggests either that our cosmological simulations are missing something important, or that our surveys have not yet reached a large enough volume to be statistically representative. The 2024 analysis by Vallard and colleagues was explicit about this. The superclusters we observe may simply be larger than any simulation box currently used in cosmology. If so, the tension is not a failure of the theory, but a limitation of the comparison. But if the discrepancy persists as surveys grow, it may point to something deeper. A gap in our understanding of how structure forms, how dark matter clusters, or how the initial conditions of the universe translate into the architecture we see around us. The Great Attractor sits at the intersection of all these questions. It is a product of the cosmic web, shaped by dark matter, measured through peculiar velocities, and challenged by the very models that should have predicted it. It is, in miniature, the story of modern cosmology itself, a discipline built on the interplay between what we can see and the far greater reality of what we cannot. And beneath all of it, beneath the dark matter scaffolding, beneath the basins and ridgelines and flows, lies a force working in the opposite direction entirely. Dark energy, the mysterious component that accounts for roughly 68% of the total energy content of the universe, drives the accelerating expansion of space itself. On small scales, gravity wins, clusters hold together, galaxies orbit within them, and the cosmic web persists. But on the largest scales, dark energy is stronger. It stretches the distances between superclusters, weakens the gravitational bonds that define the basins of attraction, and ensures that structures like Laniakea, despite the billions of years of gravitational work that assembled them, will eventually dissolve. The flows will slow, the convergence will cease, and the basins will flatten into a uniformly expanding void. Gravity built the architecture. Dark energy will, in time, erase it. It began with a warm spot in the sky. A fraction of a degree, detected by instruments strapped to the belly of a spy plane, in a signal that had been travelling since the universe was less than 400,000 years old. A gentle asymmetry, one side of the cosmos slightly hotter, the other slightly cooler, carrying within it a piece of information that would take half a century to fully decode. We are moving, not just the Earth around the Sun, or the Sun around the galaxy, but the entire Milky Way and every galaxy around it, carried through space at 630 kilometers per second towards something we could not see. What followed was one of the more remarkable detective stories in the history of science. 7 astronomers measured the velocities of hundreds of galaxies and found them streaming in the same direction. A name was given to the unseen source of the pull, the Great Attractor, and immediately the Milky Way itself conspired to keep it hidden. The the zone of avoidance, that belt of dust and stars running through the most important part of the sky, turned a gravitational mystery into an observational one. For years, the attractor existed only in the numbers, a force felt but never seen. Then the curtain began to lift. Infrared surveys, radio telescopes, and X-ray satellites pierced the dust and revealed a massive galaxy cluster exactly where the streaming motions had pointed. The Norma cluster, Able 3627, violent, luminous in X-rays, and gravitationally commanding. The heart of the Great Attractor had been found, but even as the discovery confirmed the anomaly's existence, it raised a new problem. The mass was not enough. The Norma cluster and the surrounding filaments could explain less than half the motion. The river did not end where everyone had expected. It kept flowing deeper into space. The Shapley supercluster, 650 million light-years away, emerged as the deeper source, the most massive concentration of galaxies in the observable universe, pulling not only us, but the Great Attractor itself toward it. The attractor, it turned out, was also being attracted. And on the far side of the sky, in the opposite direction, an enormous void, the dipole repeller, was pushing with a force comparable to the pull of every mass concentration ahead of us. We are not simply falling toward something, we are being launched away from nothing. Laniakea gave us a name for the structure we inhabit, a basin of attraction 500 million light-years across, defined not by boundaries drawn on a map, but by the direction galaxies flow. The Great Attractor sits at its gravitational centre, the valley floor toward which everything converges. And yet Laniakea itself may be a tributary of something larger still, a sub-basin within the Shapley watershed, a current feeding a deeper river. The scales keep expanding, and at every level, the architecture is shaped by something we cannot detect directly. Dark matter, silent, invisible, comprising 85% of all matter, built the scaffolding along which everything visible was assembled. The galaxies are ornaments. The structure is dark, and all of it, every cluster, every filament, every basin and void and flow, exists in tension with a force that will ultimately win. Dark energy is accelerating the expansion of the universe, stretching the distances between superclusters faster than gravity can close them. Laniakea is not gravitationally bound. The flows that define it are real, but they are temporary. Over cosmic timescales, the convergence will weaken, the streams will slow, and the basin will dissolve into a universe that expands forever. The Great Attractor is a local victory of gravity over expansion, and like all local victories, it is finite. There is something quietly extraordinary about that. We live in a universe that is simultaneously pulling itself together and flying apart. On one scale, matter reaches across hundreds of millions of light years, gathering galaxies into rivers of motion that flow toward common centres. On another, the expansion of space is carrying those same centres away from each other, gently and irrevocably, ensuring that the structures we have spent decades mapping are not permanent features of the cosmos, but passing arrangements. Immense, beautiful, and brief. The Great Attractor is not a single object. It is not a monster lurking behind the Milky Way. It is a region, a convergence, a gravitational low point in a landscape so vast that mapping it required the combined efforts of hundreds of scientists across more than 50 years, working in wavelengths from radio to X-ray, measuring the motions of tens of thousands of galaxies. And even now, the map is not complete. The zone of avoidance still hides a significant fraction of the nearby universe. Superclusters may yet be discovered. Voids may yet be charted. The cosmic watershed is being drawn, but the cartography has only just begun. We are part of this flow. Not observers watching from outside, but participants, embedded in the current, carried by the same forces that move every galaxy within 500 million light years of us. We cannot feel the motion. We will never see the destination. The light from the Great Attractor's centre has been travelling for more than 200 million years to reach us, and we are no closer to arriving there than we were when the first photon set out. The current is patient, the distances are merciless, and the expansion of space ensures we will never close the gap. But we mapped it. From a warm spot in the microwave sky, we traced the motion to its source, saw through the dust that hid it, weighed the mass that drives it, and discovered that the pull is only half the story. That is not a small thing. The universe is under no obligation to be comprehensible, and yet piece by piece it has yielded to the persistent, careful work of people who refuse to stop asking what lay behind the curtain. The current carries us still. It always has. And now, at least, we know which way the river flows.